Hello everyone. Let's continue our discussion on power planning. So before we enter into the step of power planning, let me try to introduce you to a problem first. So we had seen this initial problem where this particular circuitry was demanding current at the same time. Basically each and every element of this particular circuitry was demanding current, and the decoupling capacitor was supposed to provide all the charge or all the current to any of the element present in this particular circuitry. Okay, let's take this particular circuitry and keep it as a black box. Let's say that was a macro. Let's say this was a macro. Okay, now the second problem statement is, if this particular macro is being repeated multiple times on the chip, then there will be current demand for each and every element of this particular macro. Let's see what I just said. Okay, for example, that this was one of the macro, or this one of the block for which the problem was solved using decoupling capacitor. The problem of the current demand was solved using decoupling capacitor. Similarly, we have this particular macro being repeated 4 times. Okay, let's say this is your complete chip, and it has got these four macros, this macro being repeated multiple times, and there is some logic which is present at the boundaries also. Okay, now also assume that this is the driver, this is the load, and there is a signal that is being sent from driver to load, and the signal is basically logic 0 to logic 1. Okay, so what in this scenario, what we have to do is we have to make sure that this particular complete line maintains the same signal, so that the load receives the same shape of the signal. This is what we have to make sure. Okay, now let's see where the problem lies. So now let's try to connect all of them to the power supplies, something like this. You have this particular power supply, you have VDD, you have VSS. The VDD lines goes over here, it goes over here, and this blocks has been tapped to the VDD. This blocks has been tapped to VDD. Okay, and similarly you have the ground line which goes here, and all the block ground lines are tapped to ground. Okay, we see all of them, we see them for all the 4 blocks. Now assume that this particular line assume that this particular line is a 16-bit bus. Okay, and before that, when we say that this particular line has been charged from logic 0 to logic 1, basically driver is sending a signal from logic 0 to logic 1. So this complete signal, this complete line has to retain this particular scenario, so as the load should receive the same signal. Now for this particular line to retain the same scenario, it should get the necessary supply from the power, because now in this region we don't have any decoupling capacitor that will take care of this particular scenario. So since we don't have any decoupling capacitor in this area, the power supply is the one who has to supply power to this complete line. And also it's not very feasible to put decoupling capacitor on all over the chip. So some sections, some critical blocks are being decoupled from the main supply using decoupling capacitor, but not for each and every element. We can't do that, it's not feasible. Okay, so over here if you see, this particular line has to be taken care by this power supply, and now this power supply is sitting a bit at a far distance from this particular line. So there is always a possibility of voltage drop. So what you see VDD over here, that might not be VDD on this line, but it might be something else. Let's try to see how. Let's try to see what will be the value of this particular, what can be the value of the VDD and the ground at this particular point. Okay, so let's assume that this is a 16-bit bus, and let's try to take the initial conditions of 16-bit bus. So let's say this is a 16-bit bus. This was the blue line that we talked about, and this is the initial state of the 16-bit bus. So when we say the logic, the each and every line is logic 1 or logic 0, this is what we mean. So when we say one particular line of the 16-bit bus is at logic 1, it says that that's a capacitor which is being charged to VDD. Again, there is a capacitor which is charged to VDD. Similarly, for this line, whenever we see 111, these all three capacitors are charged to VDD. Wherever we see 00, these capacitors are discharged to ground. They're already discharged to ground. Now, let's take a scenario where the 16-bit bus, we just saw the 16-bit bus, where this particular 16-bit bus is connected to an inverter. Let's say this particular inverter, let's say it is connected to an inverter. Okay, now what will happen, this when you pass this particular logic to the inverter, the output of the inverter will be an inverted value of the input. What does that mean? All the capacitor which was charged to logic 1, they will all get discharged to logic 0 at the same time, and this particular capacitor which will all discharge to 0 will now all charge to logic 1. In that scenario, what can go wrong? Let's see that. So for example, let's say we will be taking a scenario where all the logic 1s, all the V's are switching from logic 1 to logic 0. Basically all the capacitances will are discharged from logic 1 to logic 0. And now since all of them happen at the same time, and we have a single ground line for the complete 16-bit bus. So since all of the capacitor will now discharge their charges at the same time, you see the ground which was supposed to be logic 0, there is a bump over here, and that's what basically is called as ground bounce. And if the size of this bump exceeds the noise margin level, it might enter into an undefined state, as we discussed in the previous lectures. And due to the undefined state, it can either go to logic 1 or logic 0. So things becomes a bit unpredictable over here. Okay, and since all of the capacitances which was charged to VDD are now discharging to ground at the same time, it's basically saying that this is one line and there are different taps, and all of the water taps are being opened at the same time. So during some point of time, you see that the water level at some area just increases. And this is particular that. So water level is supposed to stay at this level, but due to the taps opened at the same time, there is an increase in the water level for some time, and then it will settle down, but that's a different story. Okay, this is basically, this phenomenon is called as ground bounce. And let's see what happens when you try to when all these particular capacitances try to charge from logic 0 to logic 1. In that case, all these particular capacitances are demanding for supply from the main power supply at the same time. And since you have only single line for all these capacitances, you see there is a voltage drop because all of them are demanding current at the same time. It's basically there are multiple let's say there are multiple buckets and a single tap. So single tap has to supply water to all the buckets, but it has got not enough supply to provide the buckets, and that's why you see a voltage drop. That's why you see a shortage of water. Okay, and this voltage drop, as long as it is within the noise margin level, we are good enough. But if it goes into an undefined region, the things becomes a bit unpredictable. So the phenomena that we saw was causing a lowering of the supply voltage. Either the VDD which was supposed to be VDD on these lines now goes somewhere less than VDD, and the VSS, which is supposed to be 0 volts over here, it's somewhat at a higher voltage. Okay, so that's the problem that we see. And if you see the problems that we just discussed, those are coming due to one reason. The problem is the supply is being provided only from one point. If there had been multiple supplies, let's say there was a power supply over here, there was a power supply somewhere over here. If there were power supplies all over the places, then this problem would not have been happened, because now each and every line will look into its nearest power supply and get the supply from it. Okay, and that's exactly the solution for this particular problem. Let's see how. So let's say if you, in this cases, what is happening, the power is coming from the single source. Okay, it's coming only from one place. Instead, if the power had come from multiple places, that would have solved this problem. For example, something like this. Instead of a single power supply, which we saw in the previous videos, we'll have multiple power supplies. We have VDD, VSS, VDD, VSS lines. Okay, if you see, we have multiple VDD, VSS lines, and now each of them, let's say if this particular block demands this has been taken care by the decoupling capacitor. If some logic which is sitting over here demands a current, it will take the current from the nearest power supply, or it will drop its current to the nearest ground. So it did not wait from a power supply which was sitting over here, but it can tap the power from its nearest power supply. So this is the reason that you see in the recent chips, there are multiple power supplies, there are multiple VDDs and VSS ports, there are multiple pins for VDD and VSS ports. Okay, this is exactly the reason for that. And similarly, let's say there was a line which was sitting from there was a line which was going from this point to this point. This particular line will take its current from the nearest power supply. Even the 16-bit bus will take the current or take the charge from the nearest power supply, or dump its charge in the nearest ground line. So this is the logic. This is basically called as the mesh. And this is what exactly is the solution for our power. This is exactly the plan for our power. So this particular power planning, what we'll take one VSS line. Let's say this represents VSS, this represents VDD. So this will be all your VDDs placed in this fashion, and there will be again one more VDDs placed in a different direction, and they will be all connected. Okay, similarly we'll be doing the similar thing for ground as well. So you have these ground lines, you have the horizontal and vertical ground lines, and they are all tapped. Now any logic which is sitting over here will take its current from the nearest power supply, or will dump its current to the nearest ground. So this is basically the power planning of what we do. And in the recent VLSI chips, you might be seeing there are power meshes. There are lots of power meshes, and this is the reason for that. Okay, so we have discussed all of them in a separate section called as crosstalk videos. You might want to have a look into those videos. And what we'll do is, since I'm already running out of time, the next step is basically pin placement. It's a very simple step. So once we do the pin placement and the logical cell placement blockage, we are ready with our floor plan. Okay, so let's try to look into these two steps in the next video. Thank you.